In this problem, we're told a cooling fan is turned off when it is running at 850 revolutions per minute. It turns 130 or 1,350 revolutions before it comes to a stop. A, what was the fan's angular acceleration assumed constant? And B, how long did it take the fan to come to a complete stop? So before we solve this problem, let's write down the given. So what are we told? So we're told it's going to be turned off when it's running at 850 revolutions per minute. So essentially they're telling us the initial angular velocity, omega 0, right? And they're telling us it's 850 revolutions per minute. So they tell us the angular or the initial angular velocity, and then it's going to go to rest, right? So it starts at this, and then it's going to be turned off, and then it's going to go to rest, right? So they're telling us the final too. So they're telling us the final angular velocity is going to be 0 revolutions per minute, right? Because it's going to start at this and then go to this. And then it's going to go, it turns 1,350 revolutions before it comes to a complete stop. So when they say revolutions, they're talking about theta, right? So it's going to be 1,350 revolutions. So it's going to be theta. And then what are we trying to find? We're trying to find the angular acceleration assumed constant. So we're trying to find alpha, which is the angular acceleration. And then we're trying to find the time this took. So how do we want to do this? So let's go ahead and start with A, right? So A wants us to find the angular acceleration, or alpha. So what we want to do is use these variables and solve for alpha. And so you want to think about these just like kinematics, because there's a bunch of equations that are just the kinematic equations, but for rotational, for things that are rotating, right? And so just think about it like kinematics, but replace the velocity with angular velocity, acceleration with angular acceleration, and then change in x, or right, distance with theta. But the equation we're going to use to solve this one is going to be this one right here, which is omega squared is equal to omega 0 squared plus 2a times theta, right? Because notice what we have. We have final angular velocity, we have initial, and we have theta, so we can solve. But when we do this, we want to make sure it's in radians and seconds. So we got to convert all these into radians in seconds. So let's convert this into radians first. So 1,350, to convert it into radians, there's 1 revolution for every 2 pi radians, right? So if that's the case, we can just multiply by 2 pi, and it's going to give it to us in radians. So just do 1,350 times 2, which is 2,700, and I'm just going to say 2,700 pi radians. So I'm not going to multiply the pi out yet, but that's that. 0 revolutions per minute in radians per second is just going to be 0 radians per second, right? Because it's still 0, it doesn't matter. Then let's convert this one. So 850 revolutions per minute. We know that there's 60 or 1 minute for every 60 seconds. So that's going to cancel out the minutes. And then there's 1 revolution for 2 pi radians, as I said earlier. So that'll cancel the revolutions. So just do 850 times 2 pi, and I'm going to multiply this one out. So 850 times 2 pi, and then divide by 60. So 89, essentially it's 89.011, but I'm just going to say 89. So it's really just 89 radians per second. But yeah, so let me erase this, and then I'll rewrite it up here. So it's going to be 89 radians per second. And now we've got it all in the correct units. We can solve for alpha. And I wrote this as an A, but keep in mind what alpha is. It's written like this. Sorry for writing that as an A, my bad. But yeah, so let's just go ahead and solve for this. So we can minus this to the other side. So we would get omega squared minus omega initial squared is equal to 2 times alpha times theta. So I'm dividing by 2 theta now. And if we go ahead and do that, you're going to get alpha equals this right here. And so what we can do now is just plug in all our variables. So angular velocity, the final is going to be 0. So 0 squared is still 0. Minus, and then it's going to be 89 squared, right? We're just plugging it in. So this is really just minus 89 squared. So make sure the minus sign's outside of it. And then it's going to be 2 times theta, which is 2 times 2,700 times pi. So if you go ahead and do this, 89 squared, then you divide that by the bottom, right? So So yeah, so do this minus 89, you're gonna get minus 4.669 and so on. I'm gonna go ahead and round just to not 4, sorry, minus 0.4669. I had the wrong decimal place. So it's minus 0.4669. I'm just gonna round to minus 0.47. Just do how your teacher wants you to though. So minus 0.47, and then keep in mind the units. It's gonna be in radians per second squared, right? Because we have radians per second up top. And so yeah, essentially it's just gonna be in radians per second squared. So minus 0.47 radians per second squared, that's gonna be alpha, or the angular acceleration. So this is your answer to A. So yeah, this answer to A. Let's move on to B now. Let me actually write it right here. So minus 4.7 radians per second squared. Cool. So let's do B now. So what is B asking us to solve for? How long did it take for the fan to come to a complete stop? So the way we're going to do this is by using another one of the equations, which is angular velocity is equal to initial angular velocity plus angular acceleration times time. And so what you should notice is we just solve for the angular acceleration, and then we have these two variables, and we can solve. So yeah, all we got to do is plug them in, and we can just solve, because notice how this is going to come to rest. This is 0, and then this is 89, and then this is minus 0.47. So let's just plug them in and solve. And they're already in the correct units, radians per second. So this is going to be 0 equals 89, and then plus minus, so it's just minus 0.47 times t. So if we minus this to the other side, so minus 89. So minus 89 is equal to minus 0.47 t divided by minus 0.47. So go ahead and do this. 89 divided by minus 0.47. Or sorry, minus 89 divided by minus 89 divided by 0.4 minus 0.47. So if you go ahead and do this, you're going to get t equals 189.36. And so keep in mind, we did use an estimate for these values. But yeah, so we did use an estimate. You probably should use the more exact value. Just do how your teacher wants you to do. But this is just an estimate of your value. It's basically going to be 190. So yeah, just 190, and then keep in mind the units, it's seconds. So 190 seconds is going to be the estimated time it's going to take for it to come to stop. But yeah, so this right here is your answer to B, 190 seconds. This is your answer to A, and hopefully you found this useful.